everyone. Welcome to Team 13's presentation of the project for ME452 Design for Manufacturing. Our team members include Guruprasad Srikrishnan, Raghav Tripathi, Saranj Goel, Vishnuvardhan Iyengar, Vijay Venkatesh, and Rajkumar Thomas. In this project, we have decided to analyze and subsequently provide a feasible redesign of a gear pump. To give you an idea of what a gear pump is, it is a device that is used to displace or move fluids from one place to another with different pressures and speeds. It contains multiple gears meshed together in a body called the housing, wherein the fluid enters the pump through an inlet and then fills the gap between the teeth of the gears. The fluid is moved around due to the rotation of the gears. The gears on the outlet region then force out the fluid at the required pressure. The picture that you see here on the slide is a model of a gear pump that is primarily used for displacing oil, which is a fluid of generally higher viscosity. The size of the gears as well as the inlet and outlet can be changed in order to accommodate other types of fluids. We identified two major customer groups. The primary customer, which includes oil and gas industries, in which case the fluids are more viscous than water and would require more variation in flow. The second customer group is the secondary customers, which include water treatment plants, chemical plants, and some of the other sectors that you can see on screen. Here, you can see the fast diagram that we have used for our product. It can be seen that we have two major functions which include drawing fluid and regulating pressure. From the function component mapping matrix diagram on screen, it is seen that all the housings play a major role in containing fluid and preventing leakages from the pump. Further, we can see that the inlet outlet housing as well as housing 1 have the same function. This provides us with an opportunity for part consolidation.
As we have shared in the interim movie, the two major customer groups have different requirements. They would have different flow control as well as motor operation requirements. Accordingly, we have identified the corresponding modules that would require different iterations. As you can see, we have displayed the different modules that would work differently in accordance to customers' requirement. A linear assembly sequence provides a good reference for the gear pump to be assembled. In our initial assembly sequence, we have used the part name Housing 3 as the main platform part from which the assembly starts. As for our modified assembly sequence, we have modified the design of Housing 1. We have consolidated this housing with two fluid inlet outlet housing to form a bigger part called Bigger Housing 1, which evidently reduces the overall part count as well as reduce both assembly cost and time, and also delays product differentiation. Here you can see the assembly sequence in which the second sequence shows delayed differentiation. Further, housing 1, fluid inlet outlet housing, and the gaskets are the parts that will have major design modifications, which will be talked about in the later slides.
We analyzed the assembly to find the highest impact parts in the manual assembly process. Through our calculations, we found out that the fasteners take the highest manual assembly time. If we could exclude the fasteners, we can see that the gasket take the highest amount of time. As for the part selection, we decided to go for housing 1 and the fluid inlet outlet housing. This is because they have high functional importance as well as high manufacturing assembly cost. Selecting and working on these parts would provide us with an opportunity for part consolidation, which would reduce manual assembly costs and time. In our initial design of housing 1, the manual assembly time including fasteners came up to be 103.9 seconds, which is obviously very high and as a result must be reduced as much as possible. As for the redesign, we were able to reduce the number of fasteners that we need for this step of this assembly process, which subsequently reduced the number of parts as well as also enabling easier hand and tool access. We reduced the fastener count to 0, which significantly reduced the time of assembly to a mere 4.5 seconds. This was achieved by performing part consolidation. We merged together the initial housing 1 with the fluid inlet outlet housing, which was originally intended to be screwed in from the sides. For the parts to be improved by automated assembly, we selected housing 4 subassembly as it has high functional importance as well as high manufacturing assembly cost. Initially, this part cost $18.78. Here, as you can see, the initial design of housing 4 has a lot of threaded holes which indicate that we would be requiring the use of fasteners. By redesigning housing 4 to have protrusions for precision fit and removing the threads for using screws, we were able to reduce the total number of parts again and further followed some design for automated assembly principles, which include adding features to facilitate orientation due to the protrusions, adding features for easy insertion, as well as providing locating features. These changes help reduce the cost from $18.78 to $17.68. This design had no significant impact on the part function while lowering the manufacturing costs as the threaded holes have been removed.
Now let's look into the manufacturing process selection for the main housing. The main function of the housing is to house the gears while also preventing the fluid from leaking. Here you can see the drawing of the bigger housing one with the critical dimensions. The standard tolerance is taken as plus or minus 0.13 millimeters based on the current industry standards. The most critical dimensions are the inner big circular cuts for housing the gear as well as the holes for the fluid inlet outlet housing. The bigger housing one is made of steel, so the process selection for this part is shown here. The processes we were narrowed down to forging and machining. The process that was finally selected was machining. Machining was selected as it is more common and can also support tighter tolerances as compared to forging. The current version had some issues that were shown by DfM Pro. You can see the suggestions on screen that were provided by the DfM Pro software. The suggestions include avoiding sharp corners and using standard hole sizes. The total cost was $44.38. In the following redesign, we had made the changes suggested by DfM Pro. The DfM principles followed for the redesign are shown on screen. The new cost is $36.73, which resulted in a reduction of $7.65. Using the design for manufacturing guidelines shown on screen, we were able to incorporate the use of standard dimensions, avoid undercuts, avoid sharp edges, and avoid interferences.
Now we are moving on to the manufacturing process selection for housing 4. This part plays an essential role of containing the fluid and eliminating leakage in the FCMM, and thus has been chosen for the purpose of design for manufacturing. The critical dimensions for this housing are shown on the screen. The manufacturing tolerance is plus or minus 0.13 millimeters. The critical dimensions here are the main inner cavity that houses the gear and shaft, as well as the surrounding 8 holes that were initially threaded to be used for fasteners. The housing 4 is made of aluminum alloy, and the compatible processes for aluminum are as shown. Going through the different criterias, the processes were narrowed down to die casting, powder methods, and machining at the end. Die casting was chosen for the design as it accommodates step-like features effectively, making it the most suitable manufacturing process of all. Since the housing has to be manufactured by the die casting process, the model cannot be run through DfM Pro as well as through hubs.com. As a result, we decided not to make any design changes as everything seemed appropriate, and additionally, we used standard dimensions while following the general design for manufacturing guidelines. The total analytical cost for die casting is under $4 as shown on the screen.
Coming on to product service systems, from an environmental standpoint, we aim to have some circular economic partnerships where we will collaborate with industries to reuse materials from decommissioned pumps. Next, we can integrate our gear pumps with renewable energy systems such as solar power to have a lower environmental impact. Last, we can incorporate carbon neutral corporations to have carbon offset programs to reduce emissions associated with pump manufacturing. From customer service standpoint, we can include subscription-based models to provide gear pumps on subscriptions to contract-based customers. We aim to provide technical support for monitoring and replacement parts for maintaining customer relationships. Last, we have end-of-life repurposing on worn-out pumps for secondary applications like water treatment system. To conclude, we managed to optimize the following things. Firstly, we increased the manual assembly efficiency by about 40%. Second, we were able to save $0.11 per assembly. Further, as shown in the slide, we reduced the cost of manufacturing housing 1 and get a low cost of $3.99 for housing 4. As for the design critique, we want to analyze the non-selected parts for further optimization while keeping the holes and extrusions far from the edges. If we could start over again, we would like to lay emphasis on product family design, fast as well as FCCM, as these helped us to optimize the assembly sequence at the very start of the project and also helped us identify the key parts for the design for assembly. Thank you.